Like I said, my name is Benjamin Hlophe. I'm from Hlophe Engineering Technologies. We did some work on enabling the 100 gigabit Ethernet on the ultra scale boards. And the board that we worked on has got the VCU09P. Most of the silicon is the stacked silicon. And then there's a part towards the HBM devices with the superlogic regions. So the work was to enable 100 gigabit Ethernet connectivity and also enable PCIe. And then, like Adam has said, this may prove to be useful in PC-hosted Casper systems. And then also at the end, my colleague Amish will also speak about the partial reconfiguration. Just for credit, I would like to thank the following people who helped me during the design. And then also the project is sponsored by Sarao under the SKA. And the development setup, I've got a VCU 118 board. It's got 200 gigabit Ethernet links, and then of course the FPGA, and then a JTAG cable for programming, workstation, and then 100 gigabit Ethernet switch. When I started the work, I started with the VCU 118 and then eventually moved into this card, which quickly went out. This is the VCU 1525, and it changed name to Alveo very quickly. And my deliverable is on this card. And looking at the blocks, we've got a 100 gigabit Ethernet PHY, and then we've got the 100 gigabit Ethernet MAC. All the stuff that is reddish, I'm not good with colors, they are Xilinx IP blocks. So just like off the shelf from Vivado, as they are. And they actually quite work very well, and Xilinx actually abstracts this and puts it together to be one block. And then I've got the previous version of Vivado, the 2018, it's only in 2019.1 that it changed. There used to be what we call an L-bus interface, and then converting that to access stream. And then I've got a multiplexer to be able to multiplex different sources so that I can be able to send the data on the 100 gigabit Ethernet link. So this is just the test setup, and it eventually looks like this in the implementation. So again, is the L-bus to access stream converter, and the buses are very wide because we are working with very high throughput data rates. So we're using 512 bits, and the ingress, it's actually broadcast on all the receivers. So, and then it's filtered in each and every application according to UDP ports. So if you've got an application here, maybe at port 1000, port 2000, and then any other broadcast ports can be taken by the CPU interface. And there's an arbiter that actually arbitrates in the send part, so that we can actually be able to take data from any of the applications that will be sending the data. And there's three types of applications, mostly the ones that's just streaming data, which could be the sample data. And then the other one, it's more of the memory map and the CPU interface, so that we can have a CPU being able to also send a UDP or TCP IP packets, largely UDP, and then also to be an ARP responder and DHCP. And then Amish will speak about this one on the partial reconfiguration. And there's a big challenge because the bus is 512 bits wide. You've got about 64 bytes per clock cycle that you are dealing with. Basically, what it means is that each and every clock cycle you could be receiving a full Ethernet frame, and it begins to be incredibly difficult to work with the data because it's parallel, and it can vary in length. So the big thing is really when you are sending data, calculating the IP checksum takes about 10 clock cycles. And if the bus requires for you to have full utilization, if it's 64 bytes, to have at least 64 bytes per clock cycle, you can just see how much overhead you are losing just by calculating the IP checksum. And then with UDP checksum, you have to do it over the entire data stream. So Xilinx came up with a very clever idea. The bus is actually running at 322 megahertz, and that actually results in 160 gigabits per second in the fabric. So you've got enough overhead to actually play around with. And a solution also will be to use multiple senders and then funnel them through a multiplexer so that you can be able to have the aggregate bandwidth of 100 gigabits. And there's a big element that we use on the whole design, which is the ring buffers. I had to look between using FIFOs and ring buffers, and eventually just chose ring buffers for the mere fact that it's much simpler working with them. So again, the ring buffers are implemented using Xilinx dual port RAM. And then for one slot, it's about 2 kilobytes, so it can take the MTU of 1522 for Ethernet. And they can be 512 bits by 512 bits, or they can also be asymmetric, 512 bits and then have 32 bits so that it's easier to work with the data on the other side. It's just that you are losing throughput. And then also just to show when using 16K jumbo frames, the number of BRAMs increases quite a lot. I mean, just for one slot, you need 8 BRAMs compared to just one BRAM 18K for a non-jumbo frame. And then the arbiter is just a simple multiplexer that multiplexes access stream. Xilinx has a core, but I needed a core that has back pressure so that you can be able to apply back pressure because you've got different sink sources and then only one sink, and you need to be able to apply back pressure so that you don't drop packets. So then I had to do a multiplexer that will enable back pressure. And then also the arbiter, the ring buffers will give you occupancy. So we use a priority-based round robin. And inside these blocks, it looks like this. We've got the ring buffers, which have got a filter based on a UDP port. And then we've got the ARP cache, which is actually used because only on the yellow block side, you only work with IP addressing. It could be multicast, it could be just anything, and unicast. And then the ARP cache will give you the MAC address where the data is being sent. And there's also a clock domain crossing between the 322 megahertz and the yellow block clock rate, which is the DSP rate. And then there's a microplace subsystem connected to it that confirms to the, what do you call the Casper, what is it? Casper FPGA, yeah. So the bandwidth test setup, a PC cannot handle this data rate, so it just initiates transactions, and the test really is between port A and port B of the board, and then the switch will just show the graphs. And I think, yeah, that is all. We can also plug in 40 gig, so it's generic. You can put in 40 gig, which is part of the scope of my work, and PCIe. And then when you put PCIe, then you can have a number of Ethernet ports. And I'm experimenting with, once you put PCIe, you virtualize it into a virtual Ethernet MAC, and you can have an SDN-based switch, and then it converts this whole thing into an Ethernet-based system. And it may look like this if you use Alveo boards. So you've got a workstation, you've plugged in Alveo cards via PCIe, you can configure and then everything, it abstracts the PCIe away, and then you've got gigabit Ethernet, and the whole system look as one. Yeah. That's just an idea into the future that can happen. Okay. That's all.
You have time for one question, or have you like
So Bez, probably
Yeah.
you're saying the process of putting this in the tool, but
The CPU.
no, the process of putting this 100 gig, Casperizing it at the moment.
Yeah.
The stuff you've done at the moment is not fully Casperized.
Yeah, it's not fully Kasparized. Part of it has been Kasparized on the 100 gig. So the whole infrastructure now needs to actually be put into an infrastructure block that will exit. Yeah.
Okay.
Yeah.
Are you going to demo at some point?
Yeah. I will be having a demo this week. Yeah.
Oh, okay.
Yeah. Cool. Yeah. Thank you.